Hi, my name is Arthur, and today I'll present our work on assessing semantic frames to support program comprehension activities. So, whenever a software developer needs to comprehend some component, there are several artifacts that she can try to access to obtain information. For example, someone working on the Android WebView component can look at Stack Overflow posts with questions and answers about that. She can also refer to the official API documentation where you have more details about the Android WebView, or even GitHub issues where other community members discuss the usage of Android WebView. What is interesting across all of these artifacts is the presence of natural language text. And different studies in the literature have looked into how can I process the text within these artifacts such that I obtain information that facilitates program comprehension. To cite a few examples, there's the work from Fushi and others, where they used machine learning to identify knowledge types about the API documentation, where knowledge types can be used to identify directives on how to use the API or functionalities of the API itself, among other types. In a similar line, there is the work from Disorbo and others, where they look at development mailing lists and the intention behind sentences. So, for example, we have here two sentences discussing the leaky bucket algorithm, and the first one has an intention of someone proposing a solution, whereas in the second is actually someone discovering a problem about that algorithm. If we take one step back from this individual research and look at the bigger picture, what is happening is that we have several different artifacts and this need for a technique or an approach able to identify the sentence's meaning, such that we can use that for program comprehension. Our research asks the question of whether frame semantics can be used to fill this gap. Frame semantics was proposed by Fillmore, and it is a linguistic approach. To further understand it, let's go back to the Disorbo sentence. We could use the leaky bucket algorithm to limit bandwidth. As soon as we see the word use, we can ask the question of use what, and then someone would identify the leaky bucket algorithm, but someone else could ask the question of why do we want to use that, and then we would identify the purpose of trying to limit the bandwidth. Notice that as I guide you through this example, the verb use is a key element that we use to understand this sentence. And this is encapsulated in frame semantics as a frame. So in this case, we have the using frame. Similarly, the nearby elements related to this frame are captured in what we call frame elements. So for this sentence, we can see that there is an agent using an instrument to achieve a purpose. This example is encouraging, and one of our first research questions asks whether can we use generic frame parsing approaches for text used for program comprehension activities. To answer this question, we look at several artifacts from bug reports, GitHub issues, and Stack Overflow, and we applied Semaphore, a semantic parser, to obtain a set of sentence frame pairs. Two annotators looked at these pairs and classify them as valid, invalid, or whether they require some modification to the scope of program comprehension. One of our key findings for this first research question is that the majority of the frames are indeed applicable to software engineering text for program comprehension, but some of them require modification and some others are not valid. We encapsulate these findings into a tool called SE-Frame, which tailors frame semantic parsing to program comprehension. To see some of the capabilities of SE-Frame, let's look at some examples. For example, for the using frame, SE-Frame is able to identify the JNE function, which should be used to achieve the purpose of creating a Java class. Or for the causing or causation frame, SE-Frame is able to identify that X-bit hack or turning off X-bit hack was the cause of that observed behavior. During our annotation process, we also noticed that there are some frames that require some sort of modification for software engineering text. For example, run and get are verbs that have very specific meanings in software text. So what SE-frame does is that it updates the labels of the frame and frame elements related to these verbs. So in this case, we identify the execution of some target. As soon as we do these modifications, someone might ask the question of whether our approach produces correct frames and if it's robust enough. We answer these questions in 2 follow-up studies where we used a variety of artifacts and human evaluators to investigate our approach. You can find more details about this in the paper, but I can summarize that our findings identify that SE-frame can reliably extract correct frames across a broad range of software engineering text to support program comprehension activities. And given this explanation, one might ask the question of how can I use frame semantics or SE frames? And if we go back to the Sorbus sentence or the Sorbus example, if we combine the terms in a sentence with the identified frames, perhaps we might be able to disambiguate these 2 sentences as one proposing a solution and the other one discussing or reporting a problem. To give you a quick recap, we look at this need to identify a sentence's meaning across different types of artifacts, and we investigated whether frame semantics and or tool SE-frame can fill this gap such that we support program comprehension activities. I invite you to look at the paper to find out more details about our work. Thank you for your time.
Hi everyone. So in the next paper that you have is Arthur to discuss with us about his work. So Arthur, if a company or a developer would like to use your approach, what kind of artifacts do you suggest for starting?
So GitHub issues and Stack Overflow or even software requirements are interesting artifacts, especially because semantic frames that you can identify in these artifacts. And then you could use semantic frames to, for example, group information.
Oh, awesome. And in your vision, what is the biggest challenge on NLP or natural language processing to analyze software artifacts?
I think that the biggest challenge is the nature of the text. So there's specific words or there's some specific meaning to the text in software engineering. So for example, one of the things that we discuss in the paper is that how verbs such as run or get have specific meanings in software engineering. And then because of that, trying to identify the semantics of that text is more challenging. This is something that is also common in sentiment analysis, and it's a recurring challenge for natural language text.
Awesome, great. And maybe just for sharing a future vision, a future approach, how you are exploring the next steps, maybe could you discuss a little bit your future work and how to collaborate with your research projects?
Yeah, so for collaboration, we have the replication package, and there should be a Docker container where you can download the API and run it on your own. Of course, that you can reach any of the authors, and we'll be happy to help set up your environment. As future work, we are trying to use semantic frames to both disambiguate text and as a little bit of what I said in the last question, also to group information. So these are very interesting venues, but of course there are many challenges. This was just one of the first works on how to use that at scale in software artifacts.
Absolutely. Thank you so much for your answers. It's super cool. Arthur, congratulations for the work. The discussion room will start and people can join to discuss more further with Arthur. Okay, see you.